another episode of AVL Lunch and Learn, another Wednesday. And we have another guest on the show. My name is Thomas Klautz. I'm with the simulation group here in AVL North America. And I welcome today Brian McCaskey, our senior simulation support engineer, for an exciting topic. No pun intended. And yeah, Brian, you have been a long time with AVL. How
Yes,
long?
I've been with AVL for over 20 years now. In fact, I was one of the first engineers hired here within the AST group back in 1997.
Awesome. Yeah, it's an honor to have you here. It's a little bit different from what you do in your free time with Be a Podcaster. You're on camera today, and thanks for doing that. And yeah, let's jump into the topic with a quick overview of AVL, who we are and what we do. So we are a very research focused company, 68% scientists and engineers with 75 years experience in the mobility industry and beyond. We are all over the place, and Brian is joining us from the Plymouth, Michigan office today. And yeah, we are both with the simulation group. So we have a quite large portfolio of tools which you can try. But today specifically, we will be talking about the problem that we will solve in AVL Excite. And AVL Excite is a multi-body mechanical simulations tool, very established in the market. And we will be talking about a noise problem. And yeah, with that, I think we can jump straight into the topic today.
Thank you, Thomas. Glad to be here today. So just a little bit of an overview here. So I'm going to talk about the big idea for today, discuss a few of the Excite-M features and results, show the Excite-M model for this particular exercise, some of the results, and then go into some of the post-processing options that we have within our tools for root cause analysis. And then the point of this presentation was we combined forces with a company called VI-Grade, who have an NVH simulator. So we just conducted this simple exercise to prove out the transfer of Excite NVH results to VI-Grade to be able to auralize the noise results.
Perfect. Sorry, just one thing I always forget to mention is this is live, and you can ask questions and comments in the comments on LinkedIn. So whatever you might find interesting, type it in, and I will forward it to Brian here on the show. And yeah, with that, for real now. Thank you, Brian.
Certainly. So the big idea, whether we like it or not, electrification is still the dominant trend here in mobility. And of course, with that, we have the increased pressure to try to reduce development time and cost. Of course, the diversity of new e-axle designs have some unexpected problems that have the possibility there. Things that we haven't really thought about as of yet, because this is really a new sector for a lot of us. These designs are often lightweight, and of course, they're operating at high speeds and high torque levels, which can have their own problems associated with them. And then, of course, because we aren't masking these motor noises anymore, the transmission noises anymore with the internal combustion engine noises, the NVH response is now very much at the forefront of what we're doing for these development tasks. So what we need then, of course, is some simulation approach that can accurately capture these dynamic effects of e-axles to overcome these challenges that we're facing and will continue to face in electrification. So engineering, old is new. So I've been an engineer for 30 years. And for those 30 years, I've been leveraging development and technologies that have come from over 100 years of development in the internal combustion space. So it's exciting to be in this new frontier of technology, because we are on the cusp of developing new technology that is going to be moving forward for the following decades, and so it's kind of nice to be at the beginning parts of that. So some objectives that we want to try to do during this time where we're developing all these techniques. We want to be able to detect possible dangerous phenomena with these new designs and find the root causes for these problems, because again, this is a whole new ballgame for many of us that have been in engineering for 30 or 40 years. We need to be able to assess gear meshes and the bearings as well. And of course, we need to predict and optimize our NVH response, try to understand where these sources of noise, vibration, and harshness are coming from. And then finally, because we do have many problems with production and assembly tolerances, this is an area we also need to be able to evaluate and include into our simulation models as well. So, of course, benefits from this mean that we can increase our confidence in our designs way before we even produce any kind of a prototype. Again, in my old days, I remember that just putting together a mock-up of an internal combustion engine was several $100,000 just for one engine. I'm sure it's much more expensive now. So we can reduce the number of prototypes because of this. We can also reduce the amount of testing as well. Of course, that reduces overall development time and development costs, which is an important part of what we're doing in the engineering space today. So the solution that we here at AVL have is called Excite-M. Excite-M is a software that's specialized for multi-body dynamic simulation of powertrains. We have easy modeling that's supported with built-in powertrain components. We have assemblies that can automatically generate key results that we need for our powertrain durability and NVH. And then, of course, because we started out in the ICE space and we have expanded into the electrical space, we can evaluate any kind of powertrain system. So whether it be pure ICE based, some hybrid, or even a pure electric powertrain, we can simulate that as well. And these are some screenshots coming directly from our tool. So Excite-M, it allows us to create the so-called virtual twins. And this virtual twin is a high-fidelity dynamic simulation model. It allows us to be able to optimize and validate things in the virtual environment, which, of course, is going to save us time and cost. So how do we do this? We do this by using fully flexible bodies based on finite element meshes. So you can see on the left-hand side, we have several components where we do some work inside one of the FE tools to provide this information as input to Excite. We have a time domain solver that enables us to investigate all the nonlinear interactions, whether they be from the gear contacts, oil film bearings, or other components. We can also consider the oil in lubricated contacts for radial, axial, and piston liner contacts. And then finally here, we can consider the electromechanical interaction within e-motors as well, which is, again, something we're really focusing on in the mobility space today. And just to be clear, all these effects are considered simultaneously in the AVL Excite-M dynamic simulation, just as it's occurring in the real-life operation. So what are a few features of Excite? So Excite has an engineering style gear shaft modeler that allows us to define our properties, our assembly dimensions directly like we would see on a print. We also have the ability to insert predefined assemblies for planetary gear sets or even internal combustion engine assembly. We have preset internal geometry that's based on boundaries and reference dimensions. We're able to visualize predefined motion, be able to look at these structural loads. So we can see in the animation here, the kinetic animation of our planetary gear set under operation here to give us an idea of whether we've got our initial conditions and our boundaries set up correctly for this particular animation or this particular simulation. And then down below, we have our distributed electromechanical load specified on the stator. And then also another nice feature is we have so-called focus and context view technology. So we can look through slices of our components to be able to see what the dimensions are and be able to change those very easily and quickly and get immediate 3D feedback in our viewer. So the next question, of course, what are some of the main results that we can get out of Excite-M? So from an NVH standpoint, we can specify virtual accelerometers and be able to measure the acceleration at specific points to be referenced to, let's say, real testing locations on our testing facility if we need to. We can consider coupled bending and torsional vibrations and be able to get those out of the simulation. We can look at mount bushings and vibrations. We can consider the rotor dynamics, structure-borne noise, what are the velocities and accelerations of the structure, and then also the airborne noise as well. So we can see here on the right-hand side, we've got some screenshots showing some structure-borne noise of a housing of a motor, and then showing the overall airborne noise that's just emanating onto this 1 meter sphere in space. Other things we can consider, excuse me, are the gears. So we can consider gear meshing forces. We can consider rattle, whine, clunk. And you can see on the right-hand side here, we have a nice Campbell plot showing the effects there, showing rattle in the wider frequency range, and then, of course, seeing whine in that single narrow band range. We can consider dynamic transmission error. We can look at loaded tooth contact analysis and also consider power losses. And then finally, just to round this out, from the bearing standpoint, we can examine bearing forces and moments. We can look at raceway deformations and also see power losses. And we can see on the right-hand side again, we've got the radial contact forces from the at the contact at the rollers themselves. And we can also look at the order plots to see where the transmission error and forces are coming from. So for the exercises I mentioned, we wanted to do something that was fairly simplistic, but demonstrated the workflow with ourselves and VI grade. So what I did is I utilized one of our example models, which is a cylindrical gear set. So you can see here it's got a housing that's mounted on some blocks like you'd have in a test facility. And then as I did a cutaway view here, you can see the actual internal components. We've got an electric motor. We've got a 2-stage gear here, and then, of course, we've got some driver on the outside, a dyno-type driver that's moving this at a specific speed. So, as I mentioned, it's a 2-gear reduction, and what I did is I utilized a single loading condition and ran this from 1,000 RPM to 9,000 RPM at 1,000 RPM increments, and I used 2 different variants. So one of the nice things about Excite is that you can easily change the microgeometry of the gearing to be able to see what the influence might be. So in the base model, I used just regular gear geometry as it would come machined, let's say. And then I used a secondary variant, which was gear crowning with a microgeometry of 3 microns. And what I wanted to do was to really see within Excite, just with this basic model, what is the impact going to be of this modification? So here's just showing you the rotor speed at 4,000 RPM. I just chose a random speed here just to show, again, the result that once I got through my initial conditions, after a few seconds, or after a few microseconds, the simulation was steady state up until the 5-second range that I ran the simulation under. And what I wanted to do is I wanted to be able to export the mount excitations and provide those to VI grade for this exercise. So again, just from the standpoint of being curious, I wanted to see what the differences were with the model without crowning at the 4 mount points versus crowning at the 4 mount points. So you can see here in the 3 principal directions for X, Y, and Z, what each one of the 4 mounts had as far as forces were concerned. And this is, again, without crowning. And if I move to the model that had the crowning, you can also see that the forces are very, very similar. So at least this gives me some confidence that I don't have anything wrong in my model and that really the microgeometry isn't affecting something on a very large level. So I want to dive into that a little bit deeper. So what I want to do now is go into, let's say, the order content and the frequencies. So I looked at my results for the speed range again, from 1,000 RPM to 9,000 RPM, and I wanted to see what the dominant orders were. I wanted to see if I could locate and find some gear whine or maybe some rattle in this, even though it was, again, a very rudimentary example. And what I could see here is at the 14.64 order and the 27th order, I could see that there was a propensity maybe for some gear whine at that major order line. So that's kind of where I wanted to place my focus and say, okay, what if I look at the results that have the crowning included? Can I really see over the frequency range some differences there? So the next slide here shows that, and you can see for the 14.64 order that there is some decrease there And for the 27th order, you can really see that the order content there has reduced fairly significantly, at least from the eye standpoint. And I can go further and look at order tracking. So I can track those individual orders for both the baseline and the modified gear tooth microgeometry. And I can see that there were some differences between the baseline and the modified example. So again, I can have some confidence knowing that I've had some impact here in my simulation to better the whine noise that's in this model. And furthermore, I can look at the animation, the 3D animation within our post-processing tool. And again, with this, you can see the baseline and the modified at just a specific point in time. And you can see at the right-hand mount point, for sure, that there is some difference there with respect to the overall velocity at that particular location. So again, so I know that I'm getting some influence and I'm getting some benefit from utilizing this gear microgeometry on the structural vibrations. So furthermore, what I could do is I could do some root cause analyses. So these root cause analyses allow us to be able to understand maybe where the faults or the problems are coming from. And it can be very complicated, and it can come from several different sources. So first of all, it could be coming from the eigenmodes of the system. It could purely be coming from some resonance point with a bending or a torsional mode of a shaft or of a housing. It could be very simple like that. Or perhaps it's coming from the external forces. In the internal combustion area, it could be coming from the gas pressures, or maybe in the E range, it's coming from the electromagnetic forces, maybe providing some ripple or some other modes in there that we're not really expecting. Or finally, it could be coming purely from the reaction forces. Maybe it's in the gear contact force. Again, we've been talking about gear whine. Or maybe it's coming from the bearing force. Maybe there's some sort of rollover that's occurring that's causing some of the faults or the problems that we're experiencing in our model. And we can go even further into this. We have several different methods that we can utilize within AVL to dig down and try to understand where these root causes are coming from. So, for example, what is the deformation shape of the resonance itself? So what we could do is we could do a so-called operational deflection shape analysis. And what this does is it allows us to look at the actual bending and flexing of the component, whether it's the housing or the entire system, to see really what is affecting a particular portion of our model. We could also look at what excitation path is causing the resonance. We could do a numerical transfer path analysis and really dive in to see, what modal content is really driving that resonance that we're seeing. Another thing we could look at are the eigenmodes. What is happening at the resonant frequencies. We could do an operational modal analysis and really see, deep dive into the structure and see exactly what's going on there. Or even on a system level, what mode is contributing the most on the resonant vibration. So we could do a system modal contribution factor analysis where we can actually look to see what dominant mode is affecting the result of our simulation. Or finally, what component mode is contributing the most on this resonance. So we could do a modal contribution factor analysis as well. So these are just a few of the tools that we can use from a post-processing standpoint to be able to understand more clearly, what is going on with our simulation model. But when we get to this point, we kind of asked ourselves the question, and this is where we transition a little bit into what VI grade can offer. What do we do next? And the whole idea was to try to oralize or be able to hear by ear what the Excite-M model was doing from one baseline model to the optimized model with the gear profile modifications. So again, we connected with VI grade, and their mission is to help customers with zero prototypes. So a little bit about NVH. So this came from our friends there at VI. Basically, there are several different areas where we see automotive sound and vibration. Of course, we've got this whole range from 0 hertz up to 20,000 hertz. And what we can see here that in the powertrain, we typically have these type of responses that are dominating. Maybe it's engine combustion, maybe it's tonal gear and motor noise, maybe it's boom, shake, or shudder. All these things that we've heard about in our engineering days. Or maybe it's road noise. Road noise is a big thing. It could be coming from the tires and the tread. It could be coming from the structure-borne sound and vibration, or maybe some imbalance. And then finally, wind noise. Wind is another thing that we don't really think about when we're driving, but really we get that whistle, or we get that effect that happens through maybe our trim package, for example. I've got an older vehicle, and it's very noisy. I can really hear the wind some days. So. And then finally, brakes, squeals, HVAC, chimes, warnings, communications, all these things are contributing to automotive sound and vibration. And primarily from sound standpoint, we have this area on the right-hand side, which are mainly your higher frequency orders. And then on the other side of it, we've got vibration. There's a little bit of overlap, up to maybe 100 or 500 hertz down to zero for motion. And those are really where our sound and vibration are coming from. So why is this important? Of course, today especially, and if you think about it, think about a Harley Davidson or think about a Mustang. They have a very specific sound that feeds into their brand DNA that they really want to try to deliver. And when you hear something going down the road, you're like, oh, that is exactly a Harley Davidson that's going, or that's a Mustang or whatever. And so that's really where today we really have to be careful, because there are not the, let's say, the real typical sounds that we get anymore. So again, because we don't have that masking, we have to really consider the interior noise of our vehicle. What is the character? Are the drivers satisfied? They feel like they're in a quality vehicle. On the exterior, what does it look like? As far as the character goes, the soundscape. What kind of pedestrian warnings might we have? And then, of course, vehicle NVH, because this all affects our buying decisions, satisfaction, warranty, loyalty, and repeat buyers. So all these things kind of play into the whole idea that sound and vibration is really important to the consumer. So the evaluation here, of course, we all know as engineers that there are many different types of data and CAE analyses that we can conduct. And all these give us some great visual feedback. You can see here there's a nice picture, an animation showing a crash test with some body in white here. We've got some CFD flow going through a manifold up above, or even the airflow around a race car. So the whole thing here that we really were trying to work through is that NVH data really can't be fully expressed, experienced, and understood by plots, graphs, numbers, and other means. They're really useful, but qualitatively, what does it mean for us? Like, does it sound good? Is it better than the previous design? What does it sound like? And that's where VI grade kind of came in on this. So what they did is basically we wanted to evaluate our design without a physical prototype. And be able to provide some interior e-motor sound at the ear to get some idea of what kind of noise we're experiencing and how we were doing with the let's say the variant from the baseline to the one that had the gear microgeometry. So what we did, I provided VI grade with some mount operating forces. They imported those into their system, and then they applied also some surrogate transfer functions, road and wind masking noise, because that wasn't something that we had available, but they had such things available from some generic testing that they had. And then what we wanted to do is develop some plan to improve the design. So what they did, they took our mount forces, converted them from a CFSV into their software package, read them into their toolbox, and then converted them into order versus RPM amplitude data into their specialized .ord file. And then what VI grade did is they took all of these mount forces that they had imported from an order standpoint, they combined them with the driver transfer functions, and then we're able to utilize these for a simulation to be able to hear what's really going on. So I've got source strengths, transfer functions, and then the contribution coming from the actual mount itself. The nice thing was they were able to turn on and off various components as well in their software tool. So what VI Grade did is they took our model, did a virtual drive, and were able to compare the data between the baseline and the model that had the microgeometry utilized. So the next two slides are just going to show visually what the difference is between a model that has all the road and the wind masking included. So you can see here on the right-hand side, and there is a video that goes with this, but for the sake of time, I didn't display that. Basically, screenshotting showing on the right-hand side here what the order content was over time versus frequency, and then also looked at the content data of the noise itself. So you can see it's quite noisy as we ramp up and then ramp back down. So what happens if we remove the road and the wind masking noise? And this is the difference. So what we could see here is the content coming from our test before and after utilizing the gear microgeometry that we included. So this is testing. I think this is the one model without the microgeometry. But again, being able to show that you can really separate the wind masking versus the noise that was coming from our mount excursions here. So the analysis then allowed us to be able to compare both the path contributions from a transfer function standpoint and do these so-called what-if studies. So at the end, what we really proved out here was that we could evaluate NVH data efficiently using Excite-M. We could make decisions quickly and rapidly, deciding what kinds of things could potentially be problematic for us. Saves time because, of course, we now have this quick import of CA data and this NVH evaluation tool. And then finally, the biggest thing we're all trying to do is reduce cost, right? So we can use these virtual prototypes, evaluate the NVH before fabrication and manufacturing. And again, it just overall just gives us a much more refined and streamlined process. So with that, that's the end of my presentation.
Thank you, Brian. Yeah, that was great. It's really impressive what you can achieve when you pair simulation with actual hardware, so you can experience it. I think, in my opinion, this is always a great topic. And yeah, looking forward to the final results, to see this in some vehicles, like a couple of years down the road. Hopefully, they sound much better. Yeah, with that,
Yes,
um, let's see if some questions pop up still. I think so far nothing urgent, but yeah, maybe we also we of course answer them later. So post them in the comments
certainly.
at any point, or reach out to Brian or myself directly. We are always open to chat about any of the topics that might be interesting to you. And yeah, we also have this recorded on YouTube. So I think on the next slide you will find the link as well. Exactly. And also the previous ones we have recorded either here on LinkedIn or on YouTube as well. Last week we had a scenario simulator, brand new tool for ADAS. So definitely check this out if you are interested in ADAS. And the next one, next Wednesday, will be about fuel cell simulation. The month of June will be heavily fuel cell focused here in the US, with multiple events, first in Vancouver and then in Houston. And fitting to that theme of the month, we will continue with fuel cell simulation. And yeah, thanks again, Brian. And have a
Thank you.
great rest of the day and of the week, everybody. And hopefully see you next Wednesday again. Thank you and bye-bye.
Yep. Goodbye.
Okay, we're out. Very good.
Awesome.